Okay, good morning, everybody. I wanted to go through one of the Chapter 5 review problems that was not assigned as an example. Let me just grab my highlight clicker. So, looking at question 17, which I've cut from there and I've pasted over here. So we have right there we are. We've got a 1,450 kilogram car towing a trailer of 454 kilograms. We're told that the force of air resistance on both vehicles, that means combined, is 7,471 newtons backwards, and the acceleration of both vehicles is 0.225 meters per second forward. And we're asked to find the force of static friction on the wheels from the ground. So the wheels push back on the road and the road pushes forward on the wheels as a way of looking at how cars drive. So this is a generic two-dimensional free body diagram where you've got a forward force and a backward force and an upward force and a downward force. This could be an applied force. This could be, kinetic or static friction. In this case, it's air resistance. Generally, this will be gravity, and this will be the normal force. Usually, that force will be equal to that force, but not always, depending on the situation. And in this case, we have some acceleration. So we know if there's acceleration, then this force has to be greater than the air resistance. Okay, so we've got an unbalanced force. Well, F net equals ma solves every dynamics problem. What's the net force? Well, we go up here to the free body diagram, and the net force is static friction minus air resistance based on this sign convention equals mass times acceleration. Now I'm going to put in the values given in the problem. The air resistance is 7,741 newtons. The combined mass of two vehicles is 1,904 kilograms. And the acceleration is 0.225 meters per second squared. Now, I rearrange the equation for static friction, essentially adding 7,471 newtons to both sides, and I get a combined force that the static friction has to give me of 7.90 times 10 to the 3 newtons if I round this off to 3 significant figures as I need to. 3 significant figures there. There's 3 significant figures there, 3 there, there's 4 there. So I have to defer to 3 significant figures. And this setup is pretty much your setup for most of the problems you'll see. Now, it could be that one or more of these forces disappears. For instance, if this was a hockey puck just sliding down the ice, then there'd be no forward force on it. There'd just be a little bit of backwards force due to friction from the ice, perhaps a little bit of air resistance. If you're told, as in some of the problems, that the ice is frictionless, then the gravity down and the normal force up will be the only forces, and there'll be no forces going forwards or backwards. As long as there's zero acceleration, that's legit. As soon as there's an acceleration, you know you have some sort of unbalanced force situation. I also want to draw your attention how I like to set up the problem. My generic equation, F net equals ma, pretty standard. What's my F net? I go to my free body diagram for that. So if you don't have a free body diagram, how do you get your F net statement? Here's a hint, you don't. Draw the free body diagram every time. This is the key that unlocks every single dynamics problem. At any rate, I hope that helps out a little bit, and we will see you again soon.